So, Professor Sargent, you've had a bit of a great run with papers in the last couple of months.
Oh, it's amazing. The group has just achieved remarkable things recently.
Cool. So tell me what is, for you, personally really exciting about the paper that's just come out?
At an applied level, what's really exciting is that we've made the most efficient ever solar cell based on colloidal quantum dots, which are paintable or sprayable semiconductors. From a fundamental standpoint, the way in which we've done it is very original. In fact, sort of it's against what people thought could ever work.
Right. Okay, so let's break that down. Explain exactly what you did.
So until now, solar cells based on colloidal quantum dots, which are semiconductor particles, they're semiconductors that you can make in a solution and you can basically coat out of solution. It's really a pathway towards very low-cost solar cells. Until now, they've relied on kind of a layer, a protective layer, an encapsulating layer that's been based on organic molecules. Mm-hmm. It's worked very well, but one of the challenges is that these organic molecules have bulk. Mm-hmm. And when you're trying to then make a semiconductor film where electrons flow very readily through that film, having bulk, having spacers between these semiconductor particles impedes that transport.
Okay, now when you say they're bulky, most people don't think of molecules as bulky.
Yeah, so they're, I mean, we're talking about nanometers here, right? And so it's all relative. And so the quantum dots themselves are a few nanometers in size, say 3 nanometers in size. If you space them out by 1 or 2 nanometers, that looks like a long chasm to cross. That looks like a long distance for an electron to make it across. But if you can put them really close together, you can couple them really tightly, maybe half a nanometer, all of a sudden you transition from what looks like a long distance for a nanoparticle to something where an electron can readily make it across this little crack in the road.
Okay, so the reason that the electrons need to flow is because basically that's how the electricity gets off the solar cell, right?
Exactly. So when you think of what a solar cell is doing, I mean, it's taking energy from the sun, it's converting it into electrical power. Electrical power consists of a current and a voltage. The current is the flow of the electrons. They have to make it out of this solar cell for it to work.
Okay. So why do you have to coat the colloidal quantum dots in any kind of thing, whether it's a molecule or an atom?
So the key to making a solar cell that works, or one of the keys to making a solar cell that works, is what we term passivation. And let me describe first the problem that addresses. So the problem is that if you leave the surfaces of almost anything untreated or untouched, what emerges is something known as electronic traps. And what that means is that electrons will get stuck in these dead ends. It's a bit like if you were driving along the road and you were to encounter a pothole. These are sort of potholes for electrons. And the more of them there are, the more of a problem you have, and the deeper they are, just like with a pothole. If you could lose your entire car in it, that's not a good pothole. Right. So they have to be ideally absent, but if their traps are present, the lower the density, the smaller the depth is preferable. So passivation refers to the art and the science of putting layers, engineering layers onto surfaces in such a manner that these traps are minimized or mitigated.
Right. So it's sort of like filling the potholes to some extent, or coating the potholes.
Exactly. Right. And so that's what we've managed to do. That's what the organics were doing reasonably well, but they were doing it with this compromise, which is the bulk, the spacing. Right. And what we figured out how to do was to just take a layer of individual atoms. So we call it inorganic passivation because it's no longer using organic molecules. Take really the smallest imaginable passivating layer, which is just this overcoating of one layer of inorganic atoms, and to use that in order to passivate the surface of these particles.
Okay. So that reduces the distance between the electrons, it reduces the number of potholes and the depth of the potholes, that increases the flow, and that's why you got an efficiency of 6%, which is great, right? That's
right. So that takes us back to why this is important from an applied standpoint. Mm-hmm. The lead author on the work, Dr. Jiang Tang, figured out both a new material strategy and something that was really kind of not something that anybody had succeeded in doing before. The community had been building solar cells with good success, good progress based on these organic molecules. Jiang took this kind of countercultural view and he said, I want to do this using inorganic materials because ultimately they offer the pathway, a prospect towards the the best possible packing, and he believed that we could find ways to achieve passivation this way as well, and he did. And so not only did he kind of turn the field upside down with this new strategy, but he also broke the record at the same time.
Right. And that's pretty astonishing that first thing out of the gate is a record setter, right?
It's very unusual, and the other thing that was just so nice about it is that the science is so interesting. I mean, we worked with our partners at Penn State and also at KAUST to understand why this works. And we were able to use techniques to actually measure these traps and look at their energy depth and their density quantitatively with our Penn State partners. And with our KAUST partners, we were able to show that it was that passivation that was the key. It was the bringing of these materials into this sort of condensed form and combining it with the passivation. It was that did lead to this performance advance.
And the other advantage of doing this the way you're doing it with the passivation with the inorganic molecules or the atoms is it reduces the cost of production, right? You're doing it at room temperature very simply, relatively simply. Right?
That's right. I mean, that's the key challenge for the field of photovoltaics is to not have either or between high performance and low cost, but is to unite those together. And the approach that we used here was carried out all at room temperature, just involved basically coating a semiconductor onto a substrate at room temperature. So when you think of the ways in which we make silicon solar cells today, or even the ways we make thin film solar cells, which are a lower cost, a lower energy consumptive approach. I mean, even the existing thin film technologies involve cooking things at 400, 500, 550 degrees C. This was done all at room temperature.
Right. So it's equivalent to sort of an offset printing or roller-to-roller kind of printing, right?
That's right. I mean, just picture the way you print a newspaper. It involves like a serial process. Mm-hmm. It can be extremely automated. That's good for manufacturing cost. Our materials costs are very low. And then actually, probably the biggest factor that really needs reducing in the cost of solar cells today is what we call the balance of systems cost. That's the cost to deploy a solar cell. Imagine taking something that's got layers of glass, it's very heavy, and hauling that up onto a roof. Mm-hmm. That adds to the cost of installation and even sometimes reinforcing the roof. But when you have a technology where the layer, the laminate is very thin, it's very lightweight, mm-hmm. and it's on a flexible backing, all of a sudden you have a real strategy to reduce these installation costs.
Right. So do you imagine it's still years away before we actually buy these at Rona and Home Depot, or is it sooner than that? What do you think?
We've got some work to do. There's a number of steps we have to get through first. So the first one is that we need to make further progress on efficiency. The 6% number is exciting because it's a record for the field, but the community generally believes that one needs to get above a 10% power conversion efficiency to have something.
And the solar cells that are deployed now, there are efficiencies higher than that, right? It's around 40 or so?
So the solar cells that are actually deployed are between 14 and 18%.
18, sorry.
So we're striving to get close to those numbers. Of course, we have a pathway through these materials to reach them and to beat them. But we believe that even as we start to approach them, because of the combination with the low cost and the low installation cost, we have something very exciting.
Mm-hmm. Great. Thank you very much for filling us in on it.
Great. Thank you.
Okay. Take care.